Chapter 6 is called Areas, Volume, and Simple Sums. We will actually focus in on areas and summations to build up tools that we're going to be using later. The idea of integral calculus is actually based on two main problems. The first problem is the problem you probably have seen at the end of Calculus 1 class, finding antiderivatives. So it's like anti-differential calculus. If we have some function, the idea of an antiderivative is that we would like to find another function g so that the original function is produced by its derivative. This, for example, in Calculus 1, you might have seen a few rules that concern antiderivatives of power functions or other simple functions. If I have to take a derivative of x squared, I will end up with 2x, and the reverse process is called antiderivation, which is generally more complex and is something we're going to come back to towards the end of this course. The second problem is closely related to the first one, although not obviously so, is finding the area under a specified curve. So if I give you a specific function here, let's call it, for example, y equals f of x, and some two boundary points, let's call them, for example, a here and b here, the problem is to find the area above the x-axis and below the curve. So the area that is shaded in purple here. In this course, we will focus in on problem 2 first and then come back to discuss how it relates to problem 1 and how the two of them connect together. Now, if we're going to start looking for areas, let's think about some known areas that we already can compute exactly. Think of what is the simplest shape whose area you know as a formula. This is most likely going to be a rectangle. So if I have a rectangle, I can identify the sides, let's call them, for example, A and B, or length and width if you wish, and then the formula for the area is A times B. This is the simplest area formula, and that is because it actually comes directly from the meaning of multiplication. If I think of B as B units of some length, and I think of A as A units of the same length, so let's pretend that all of my divisions here are equal, then if I split this up into a grid, A times B is exactly the number of the little squares that get produced. The next simplest shape is likely going to be a triangle. The formula that we are all probably quite familiar with is half base times height, where the base is one side and the height is going to be a perpendicular dropped from the opposite vertex. These two formulas and these two areas are in fact very related. What we can do to see that clearer is to place this triangle inside a bigger rectangle. And then what you notice is the area of my bigger rectangle is base times this height, because this is the same as the side here. And this triangle occupies exactly half of my bigger rectangle. You can see that by realizing that this little triangle is the same as this one. So there's two of them here. And this little triangle is the same as this one. So there's two of them there. So these two pieces that we do not care to include in area are exactly equal to the two pieces of our triangle. Therefore, the area of the triangle is exactly half of the area of the bigger rectangle. This is how we can derive an area for a triangle. What about more complicated figures? So, for example, what about a hexagon? The hexagon has 6 sides. So here, let's draw a regular one, or at least somewhat of a regular looking one, with equal sides. Let's pretend that these are all equal. I can't really draw all that well freehand here. How can we compute the area of this figure if the only two other figures we're working with are rectangle and triangle? One idea is to dissect this into shapes of the areas that we already know. Dissecting a hexagon into rectangles might be difficult, but dissecting it into triangles is probably something that can be achieved fairly easily. I can pick a center and then I can simply divide the whole thing into triangles. Now the problem gets reduced to the one whose solution we already know. Each of these triangles can be computed using the previous formula, and then we simply have to add all of those numbers up. The idea is very simple, but its implications are very strong, because that means that you can dissect any polygon into triangles. No matter how many sides I decide to introduce, I can always divide a figure into triangles and then apply the triangle formula to it. So it seems that our problem is already solved. If this can be done for any polygon, then any figure with straight sides can be solved using this approach. What about figures with non-straight sides? What about a circle? The idea of approximating the area of a circle by placing a straight line figure inside of it was first studied by Archimedes in 250 BC, so over 2,000 years ago. The idea is really quite simple. Place a polygon inside a circle. The more sides it has, the closer the area of a polygon will be to the area of a circle. Notice that here I'm missing quite large chunks of the area of the circle, but here the chunks become smaller and smaller. The more sides, the better the approximation. And this is kind of similar to linear approximation or Newton's method or Euler's method that we have already seen in this course. The smaller step sizes you take, the better your approximation is going to become. And here, the step sizes, you can think of the lengths of the sides of the polygons. So once we, for example, decide that this is the polygon that we would like to approximate the area of a circle with, I now have to calculate the area of one triangle and then multiply it by the number of triangles that I've already created inside. So that's what we're going to do here. Let's take a look at one of these triangles that fits inside. For example, this guy. They're all the same. The polygons are going to be, in fact, all regular, so all sides being equal. So let me basically draw in a zoomed in version of this triangle here, a little bit rotated onto the side to make it easier to visualize things. What we know of the circle itself is a radius. The radius goes from the center to the circle itself, so we notice that both sides of our triangle are in fact radii of our circle. Now, in terms of computing the area of this as the triangle, the radius isn't going to be particularly useful here. The side that we have here as the base, let's call it B, is going to be useful, and so is the height. So if I drop the height from the top here, this is going to be it. This is the height, and then I can already write down that the area of one triangle is in fact 1/2 base times height. Now, I have a whole bunch of these triangles here. In fact, I have exactly as many of them as the sides of my polygon, right? So if I start off with a square that has 4 sides, going from the center of the circle, I'm going to create 4 triangles. If I have more sides, I'm going to create more triangles, but it's always going to be exactly as many of them as there are sides to the polygon. We are going to create a notation and call that n. N-gon is a polygon with n sides. So n stands for the number of sides here. So if the area of one triangle can be found, then the area of n triangles is of course going to be exactly that same number, but now n times. Now we already noticed that the more sides, the better the approximation. And we are hopefully quite comfortable with computing with more being tending to infinity. What if I set the number of sides to be infinite, so they each become very, very infinitesimally small? That means that I would like to be computing all of this above information for n tending to infinity. What happens to my R, H, B, and n as n goes to infinity? Some things I can notice, for example, is as my triangles have smaller and smaller bases, the height h here starts tending towards the radius r, right? Think of how this triangle is going to become very, very skinny, and you will realize that the height of this triangle is now very, very close to the radius. So as n goes to infinity, the height tends to r. And what else do we have? Now, if h goes to r and I'm interested in the total area, then I'm also interested to what happens with this b and n. So let's think about b times n. What does that tend toward? B was the length of the base, which means the length of each one of these triangles, and n was the number of these triangles. As these lengths become shorter and shorter and shorter, they start approximating the circle more and more and more. And adding all of them up will mean that I'm actually approaching the circumference of the circle. The circumference of the circle is 2 pi r. So now what I'm going to do is substitute both of these into the calculations for the area of my n triangles and recognize that the entire area of the circle in fact approaches or equals to the area of n triangles as n tends to infinity. Now, what is that going to be? So let's see. This h tends towards r, and this b and n together, as we've just discovered, tend toward 2 pi r. So altogether, I'm going to have 1/2 times 2 pi r for b and n times r for h. 1/2 times 2 pi r, that comes from b times n, times r for h. And what do we have? I notice that my 2's can of course cancel out, and I can combine my two r's together. Pi times r is altogether pi r squared. Isn't this amazing? We can derive the well-known area of the circle formula that has always been given to us as unquestionable truth by just thinking about fitting polygons inside the circle with more sides for better approximation. This is in fact a very powerful idea. We will use a very similar approach to calculate areas under curves by making intervals. We're going to consider them small enough that the stop is basically a straight line, and therefore the shape produced under the curve is in fact a little rectangle. Now, before we do this in more generality, we also will need to develop better notation to deal with more complex figures. The first one of them is a notion of a sequence. A sequence, simply put, is a set of numbers written in a row. So I can have, for example, 1, 2, 3, 4, 5. This is a sequence, probably a sequence that gets used a little too often in people's passwords. I can also have a sequence, for example, 1, 2, 3, 4, 5, ... where the ... signifies that whatever pattern I have at the beginning of the sequence carries on forward. The first sequence here is what we would call finite because it ends. It only has 5 pieces to it, 5 numbers. And the second one is what we would call infinite because it goes on forever. Now, sequence in general is just a set of numbers. Sequences we will always consider and be interested in are the ones that have a pattern to them. And this is something we're going to discuss on the next slide. Now, normally, you have to include enough numbers to be able to, in fact, understand what that pattern is. So if I write down 3 and 6, ... what do you think the next number in the sequence is going to be? Is it going to be maybe a 12? Maybe I'm multiplying by 2 to get from 3 to 6, from 6 to 12. Or maybe I am adding a 3 every time. That way, the next term in the sequence has to be a 9. That's not clear. So if we are going to use this dot 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 notation because we cannot write infinitely many numbers, we gotta do so carefully in order for the pattern of the sequence to become obvious. Now, the sequences that we're gonna work with, a lot of them will have specific numbers, but some of them will be defined in more generality. A1, A2, A3, and so on. These are called terms. Every number in the sequence is called a term. So more generally, if I label them with variables, each one of these will be called a term. So let's label that. This whole thing is a term. And the subscript on it is called an index. The subscript, notice, always starts at 1 and actually tells us which term in the sequence we're at. So for this sequence, for example, if I assume 12 is the next number, 6 will be the term in the sequence and its index will be 2 because it's the second term in this entire sequence. This is all of the actual terminology we're going to need. What we're going to work with next is arranging or being able to write down explicit or general formulas for sequence that basically shows us what a pattern is. We would like to come up with a way to describe the kth term in the sequence, so the kth number, as some function of that position k. Before we go in one of the directions, let's discuss the simplest one. So if I give you a formula, how can we understand that? Coming up with formulas is much harder than being able to translate them into numbers. So what this formula is saying is that the kth term of the sequence is always computed as 1 over k. So I can think of the first term of the sequence, the second term of the sequence, the third term of the sequence. Let's say I'm gonna do the first 5 and then say dot dot dot. So for the first term in the sequence, I plug in 1 in for k. I'm going to get 1 over 1, which is just 1. For the second term in the sequence, my index is 2, so I'm going to plug in 2 for k, and I'm going to get 1 over 2. For the third term in the sequence, I'm going to plug in a 3, because that's now my index, to get 1/3. And this is already kind of enough to see the pattern and hopefully be able to carry forward 1/4, 1/5, and so on. Some sequences are a little trickier to write down numbers with than others. So here I have -1 to power k. So once again, for the first few examples, I will be writing down the indices to keep track of it, but generally once you get the hang of it, you don't have to do quite so much of the actual annotation. So what am I gonna have here? For the first term, the index is 1, so I plug in 1 for k. I'm going to get -1 to power 1. For the second term, k is equal to 2. I plug in k equals 2 here. I'm going to get -1 to power 2. -1 to power 3, -1 to power 4, -1 to power 5, and so on. This seems like an odd sequence. Why would anybody ever care about this? And that's because we're looking at it, as of right now, with unsimplified terms. Let's actually compute these numbers and see what they will yield. -1 to power 1 is -1. -1 to power 2, remember that even powers will in fact absorb the sign, so -1 to power 2 is going to be 1. -1 to power 3, being an odd power, is going to be -1 again. -1 to power 4 is 1, -1, 1, and so on. So what we have is the actual number doesn't change, but its sign goes from negative to positive every single time. This is what we would call an alternating sequence. And that is because the values are alternating between negative and positive every single term. Let's take a look at this next one, k plus 3. So the index plus 3. when k is equal to 1 for the first index, I'm going to get 1 plus 3, which altogether is a 4. For the next one, when k is 2, I'm going to get 2 plus 3, which will result in a 5. When k is 3 for the next index, 3 plus 3 is 6. And I in fact notice that all it does is from now on, the sequence will always increase by 1 because the index increases by 1. So I'm simply going to have all the numbers from 4 and up. This last one in this example list is k divided by 2. Again, k being my actual index. So when k is 1, I get 1 over 2. When k is 2, I get 2 over 2. When k is 3, 3 over 2, 4 over 2, 5 over 2, and so on. Notice that I also can simplify this sequence by, in fact, evaluating the numbers, particularly the even ones where I can actually perform the division on 2. But if I replace these numbers with the simplified version, the pattern is not going to be as obviously seen. So oftentimes we do see the sequences presented in a more calculator-ready form and not yet evaluated, because it does make the pattern clearer to see. Now, going the other way around is actually generally more complicated. So if I give you a sequence and I ask for a formula, we need to discover what the presented pattern actually is. And this requires a bit of practice. So for example, this one, 2, 4, 8, 16. In fact, before I do them, I strongly encourage you to pause the video and try these guys out for yourself, as we would normally do if we were in a face-to-face class environment. Now, if you've tried them on, you would have spotted some patterns here, and some are more complicated than others. Let's say for the first one, 2, 4, 8, 16. It looks like I'm multiplying by 2 every single time, and I can also think of that as taking powers of 2. So this is like 2 to power 1, 2 to power 2, 2 to power 3, 2 to power 4, and so on. Now my indexing actually starts at 1, so my first term is 2 to power 1. My second term is 2 to power 2, and so on, which means that I can generalize and say that my kth term is 2 to power k. Once you come up with the formula, you can also double check yourself to see that whether or not it makes sense. So for example, is it true that A3, so the third term in the sequence, is going to be 2 to power 3? Yes, that seems to work out. You can always plug in 1 or 2 terms just to make sure that you didn't, for some reason, shift the index a little bit or something like that. Let's take a look at this next guy here. It looks like I have the exact same sequence as above when I'm just multiplying by 2 or dealing with powers of 2, except for this time it starts at 4, not at 2. So what I have is 2 to power 2, 2 to power 3, 2 to power 4, 2 to power 5, and so on. So for the first term, when k is equal to 1, this is k equals 1, I have the power of 2. When k is equal to 2, I have the power of 3. When k is equal to 3, I have the power of 4. So whatever my k is, the power is always 1 more. And that gives me the idea that this sequence can be described as 2 to power k plus 1. So whatever my index is, I'm going to add 1 to it, raise the 2 to that power, and that will produce my sequence. Plug in a couple of terms, make sure that the sequence matches this formula. Now for the third one, it actually is the exact same as the first sequence, except for I have this minus plus minus plus minus plus pattern happening. So I'm going to try to add this alternating sequence term to the pattern of the first sequence in order to produce a formula. And this is generally done is exactly in that way. I'm going to introduce the plus minus by allowing -1 to be raised to power k, which will go from even to odd every single time. And then the pattern for the numbers themselves is exactly like the one in the first example. So this is just going to be 2 to power k. The one thing you have to be careful about with alternating series is to make sure that you're actually starting off with the right sign, whether it's negative or positive. And what we need to do is simply check one of the values. If k is equal to 1, this is going to be equal to 1. Negative 1 to power 1 is negative, so I expect to see a negative here. If my sequence was the other way around, so if I had 2, negative 4, 8, negative 16, then the corresponding formula would have to adjust for that in a similar way that we adjusted for k here. It would have to be negative 1 to power k plus 1, so that even numbers become odd and odd become even, and then still 2 to power k. Notice that the numbers themselves didn't change, only the signs changed. So pause for a second here and really think about why those two things describe these two sequences. For this next one here, this example is similar to the last one on the previous page. I noticed that the numbers are not simplified, and that is in fact for our benefit because I can see the sequence on the bottom. In fact, if I probably write 1 over 1, it's going to be a little easier to see still. 1, 2, 3, 4, 5. It looks like the denominator is always just the position, so the k itself. So for this, I'm expecting to see k on the bottom. What about the top? I have 1, 2, 4, 8, 16, so something very similar to what we've seen before, except for it doesn't start with 2, it starts at 1. So it's kind of like the same as this sequence, except for not shifted to the right, but rather shifted to the left. So I'm expecting to see powers of 2, but the powers of 1 degree less. Again, this takes a lot of practice. So just because I've been able to come up with a formula in a matter of 20 seconds doesn't mean that I expect you to. I've seen a ton of these examples, and these are the ones that I've written myself. So spotting patterns is a truly difficult task that requires quite a bit of practice. Do take a look at web work and try a lot of these out for yourself. You will get a hang of it, I promise. For this last one, I'm simply going to write down the formula. In many ways, this is more complicated than we would normally consider for coming up with the formulas, because this is a little bit nitpicky where you have to be careful about all the powers, but do take a look at the formula and see if you can reproduce this sequence back. Next time, we will take our working knowledge of sequences and start thinking about not just listing numbers, but rather also adding them up as we go.